So this is our first flipped lesson. Let's go ahead and see how this works. Today I'd like to talk about what standards are and why we need standards. This is standards of measurement we're talking about. And as we'll see, a good part of it has to do with the French. Not maybe as much as I usually like to blame, but a good deal of it is still designed and standardized by the French government. First of all, then, measurement. Why do we need even to care so much about measurement? Well, take just a second and see if you can figure out what happened to the Mars Climate Orbiter. It was a spacecraft sent by NASA to Mars in the late 1990s. So just take a minute and pause the video and look that up. All right, so as you probably found then, the Mars Climate Orbiter actually this was millions of dollars wasted when it was supposed to arrive at Mars. It misfired, the thrusters misfired, and it missed target. So an investigation of what happened found that the scientists and engineers who had written the software and the scientists and engineers who had built the hardware had assumed two different measurement systems being used. One group assumed the international system units were being used, and one group had assumed that the American customary units were being used. And since these two systems are different from each other and no conversions were made, the spacecraft missed Mars. So it is important then to keep track of these things, including dimensions. Now, a dimension is going to tell us what is being measured. Some examples of this would be time, length, speed, weight. Really anything that we can measure has a dimension. That's telling us what is being measured. A unit is a word that is going to tell us the dimension and the system. For example, we can measure length in feet in the American customary system, or we could measure length in meters in the SI, the International System units. So the SI system, what exactly is it? You may not have heard of it before, but it shouldn't be anything new. It came into its modern incarnation in 1960. The French name for that is shown there, but you can call it the International System. And what it is really is the metric system. It's the modern day metric system, which you probably have heard about in elementary and middle school. It's interesting to note that the U.S. is the only industrialized modern nation that does not use the SI system for day-to-day work. We do use it in science, or at least we should use it in science, so that problems with the Mars Climate Orbiter do not happen anymore. So we will in this class be using liters and meters and international system units. One of the great things about the SI system is that it's easier to use than customary measurements. For example, how many meters are in a kilometer? 1,000. How many grams are in a kilogram? 1,000. Whereas if we're trying to think how many ounces are in a pound, I believe that's 16, or how many feet are in a mile, that's 5,826, 62, probably not even close, but that's my point. It's more difficult to remember the conversions in customary units than it is in the SI units. There are 7 SI base units. For length, there's the meter. For time, there's the second. For mass, there's the kilogram. Now, if you have not yet listened to the Radiolab episode about the history of the kilogram, go ahead and listen to that right now. It's a great story, but hopefully you've already done that before looking at these slides. That is the kilogram there over on the right. Amount is measured in moles. Temperature is measured in Kelvin. So these first 5 base units here we will be using in chemistry. The last 2 not so much, at least not at this level of chemistry. That would be current measured in the ampere and brightness measured in candela. these units can be combined with the other base units to get derived units. For example, if we're measuring speed, we might use meters per second. So that would be taking meters and dividing by seconds. We can take speed and divide it by time again to get meters per second, which is the unit that is used for acceleration. When we are using the SI system, a good thing to keep in mind is prefixes. Prefixes, as you've learned in English class, it's a small word on the front of a larger word. And a prefix in this case can be attached to the base unit to specify a larger or smaller amount. For example, you could say 5,000 meters, or you could say 5 kilometers. Kilo means 1,000. Hecto means 100. Deca is times 10. Deci is 1/10, like a decimal. Centi is 1/100th, like a cent, 1 cent in our money. And milli is going to be 1/1000th, like a milliliter or a millimeter. Some other ones that are good to know: mega. Mega is going to mean 1,000 times 1,000, so 1 million. Giga will be a billion. Tera would be a trillion. Going the other way, smaller and smaller, micro is going to be 1,000 times smaller than milli. Nano will be 1,000 times smaller than that. And pico will be 1,000 times smaller than that. So that's getting into measuring very, very small amounts. It's good to be able to convert things in the SI system. And it's easy because it's so much easier than our customary units, as I talked about earlier. Because in the SI system, we move by powers of 10. So kilo to hecto, we're doing 10 times, we're referring to 10 times smaller. A good way to remember this, and it's a quick way to convert between these things, is this mnemonic: King Henry died by drinking chocolate milk. So that's kilo, hecto, deca, base, deci, centi, milli. Now if you write that out, just K, H, D, B, D, C, M, this will provide a nice simple way to convert. For example, if we're going from meters to kilometers, we would start on base and we would go 1, 2, 3 to the left. So you would take the decimal point in your number. Let's say that we have 500 meters. Move the decimal place 1, 2, 3 places to the left is 0.5 kilometers. And so on like that. We'll work with that next time in class some more, but make sure you get it into your notes right now. Scientific notation. In chemistry, we're going to be dealing with some numbers that are very, very big and some numbers that are very, very small. If we had to write out all the zero placeholders involved, it would take a very, very long time, and then we'd have to go through and count them. So there is, in science, we can use scientific notation. You may have seen this already before too, but let's go through it. The general form is going to be a number, point, another number, times 10 to the power of a third number. That third number can be positive or negative. Negative if we're going smaller, positive if we're going larger. A couple of rules you should keep in mind. The first number, the A in the general form there, can't be bigger than 10 or less than 1. It's going to have to be between 1 and 10, not including 10. The C will tell whether the decimal place slides left or right. And you're going to use this, while you could use it for a nice simple number like 10, you can even express 5 in terms of scientific notation. We're not going to do that very much because that's a more clumsy way to express it. Let's do a quick example and we'll work some more with this in class. Express 525,600 minutes in scientific notation. Take a second and see if you can do that. So, you should have gotten 5.256 times 10 to the 5th minutes. Don't forget units. If you don't have the units, it's not science. Science needs units. If you didn't get it, that's fine. We'll go over it in class tomorrow. Again, this is the first video, so I just want to make it clear. This is mostly for you to get it into your notes. If you really can't wait for tomorrow and you want to learn more, check your book. You should be reading your book anyway. One last topic on today's video is going to be about measuring with accuracy versus measuring with precision. We do need both of these. So what is the difference? Accuracy is how close you are to an accepted value. If you are playing darts, for example, you're trying to, in many cases, get as close to the center as possible. So how close are you to that accepted value? Precision is how repeatable is your measure. How sure are you that what you measured, that what you did is actually how much of it that you had? Let's say that you were measuring out a certain amount of a chemical and you got a number. How do you know that that's the real number? How do you know when to round, for example? Both of these are important. The examples that you see on the right there, the one on the top left, the one labeled 1, that one is not accurate or precise. The darts are not close to the center and they are not in the same place. The one to the right of that is accurate but not precise. If you average together all those points, they would hit in the middle, but none of them are close to each other. The one on the bottom left is precise but not accurate. The darts are all pretty close together, but they are not near the center. And the fourth one is accurate and precise. We want to strive for both of those. Now, precision is going to help to explain something important, namely why I do not like math class. Now, don't get me wrong, math is very important, but math teachers like to use fractions, and fractions do not keep track of precision. They have what's called infinite precision. If a math teacher has you write out 1/3, you're probably going to write 0.3 repeating, right? That repeating sign has no place in science. And we'll go through that. Because that doesn't happen in real life. There is a limit to what you can measure. There is a limit to which we can just say, we're not sure that that number is correct anymore. If you go too many places, 5.267583295 meters per second, you couldn't actually measure that far. We keep track of precision with significant figures. This is probably the most complicated part of this first chapter, so just get these notes down and we will go over them in class. All non-zero digits are significant. Zeros at the front are not significant. Zeros at the end of a number to the left of the decimal are not significant. Zeros at the end of a number to the right of the decimal are significant. They do track precision. Zeros in between significant digits are also significant. Just get the rules down. We'll go over this next time. Again, this is in your book. Multiplication and division. If you are multiplying and dividing, your answer cannot have any more significance than the least significant factor that goes into it. In addition and subtraction, you need to keep track of precision, significance, by making sure your answer does not have any more decimal places than the factor with the least number of decimal places. That's going to do it for today, and we'll go over these in class. Thanks for listening.